All right, so today we are going to talk about velocity. Kind of touched on velocity last time when we talked about reference frames and displacement, but we're going to go more in depth today. So what is velocity? Well, remember in the last lecture we talked about the difference between a vector and a scalar, and I mentioned speed and velocity. So speed is how far an object travels in a given time. So you take the distance traveled and you divide by the time elapsed. Doesn't matter what direction you're going in. You could be going to the moon and back, but your speed will just be the total distance traveled over the time it takes. Velocity includes a direction. So when you measure velocity, it does matter what direction the object is moving in. In this case, you take the total displacement. Remember displacement? And you divide by the time elapsed. So which one of these is a scalar and which is a vector? Well, remember, scalars do not have anything to do with direction. So speed is a scalar. Velocity does depend on direction, so this is our vector. So, for definition, velocity, abbreviated little v, is a vector quantity and is defined as the displacement per unit time. So, how far an object was displaced in a given time. It's important to note that because velocity is a vector quantity, it has both magnitude and direction. So if you write down a velocity as 20 meters per second, and you do not indicate in what direction it's moving, that's only half of a right answer. So, examples of velocity are 20 meters per second down, 50 miles per hour east, etc. We define velocity as this crazy looking equation. V equals delta x over delta t, which is equal to x final minus x initial over t final minus t initial. So let's break this down a little. V is velocity. What is delta x again? Delta x is displacement. We read delta x as the change in position. And delta t, here delta stands for the same thing. It means change. But instead of change in position, the t stands for time. So this is our change in time. When we measure the change in position or the displacement, you take your final position and subtract the initial position. The same with time. When you have a change in time, you take your final time and you subtract the initial time. There are two different kinds of velocity. There's instantaneous velocity, and there is average velocity. Instantaneous velocity is our velocity at any given instant. So if you're running and someone takes a picture of you, in that given instant you had a certain velocity. That would be your instantaneous velocity. Average velocity is the displacement per unit time and depends solely on final and initial position. So if you're running across a field, let's say a soccer field, you can speed up and slow down and speed up and slow down, but your average velocity only depends on where you started and where you ended and how long it took you to get there. It does not matter how fast or slow you were going in between and how much your velocity changed. So average velocity can be found using this formula. So this formula is average velocity because it is the displacement over a given time. It does not take into account how much your velocity changed in between your starting and ending points. Or you can take a mathematical average. And you take the initial velocity plus your final velocity and divide by 2. Just like we looked at displacement versus time graphs, we will need to look at velocity versus time graphs. And they are a bit different, but it turns out you can get one from the other. So we can make a velocity versus time graph given this displacement versus time graph. So let's look at this. We have displacement on the y and time on the x. If we were to break down each leg of this journey, this is how it would read. Part 1. A student walks away from the origin, so start here, and they walk away to a displacement of 8 meters in 10 seconds. So that's part number 1. Part number 2 says the student then stands still for 10 seconds. If they stand still, displacement is 0, so it should still be at 8. However, time continues to move on for another 10 seconds, so that's to 20 seconds. Part 3 tells us the student walks 4 meters toward the origin in 4 seconds. Remember, the origin does not mean the origin on the graph here. It means the starting point. So instead of moving up away from 0 here, we're going to move back down 4 meters. So we move from 8 to 4. And how long did it take? 4 seconds. So that goes to 24 seconds right here. That's part number 3. Part number 4, the student stands still again for 6 seconds. Remember, standing still means there's no change in displacement, but time continues to move for 6 seconds. And finally, the student walks away from the origin to a displacement of 14 meters in 5 seconds. Here, 14 meters is the total displacement. It's not where you start plus 14, it's the total. So the student walks to 14 meters, which is right here, in 5 seconds. So we go from 30 to 35. That is our last spot. So this is our displacement versus time graph. Now, to figure out velocity versus time, we need to use our handy-dandy equation for velocity. Remember, it is velocity is equal to change in position or displacement over a change in time. So, for each part, 1, 2, 3, 4, and 5, we can figure out the average velocity of the student traveling. Let's do it for number 1. Velocity is a change in position over a change in time. What was the change in position? Well, they started at the origin, which was 0, and walked to 8, so the total displacement was 8 meters. And how long did it take the student to do that? Started at a time of 0 and ended at 10 seconds, so it took 10 seconds. So the velocity of the first leg is 8 divided by 10, which is 0.8 meters per second. And we can do the same thing for each of the other parts. Part 2 should be pretty easy. The student then stands still for 10 seconds. If they stand still, what is their displacement? 0. Anytime you have a 0 divided by something, multiplied by something, doesn't matter. Velocity is 0. If you do not move, you don't have a velocity. So which other one here is going to also be a velocity of 0? Number 4. The student stands still for 6 seconds. Velocity equals 0. So let's backtrack and try number 3. The student walks 4 meters toward the origin in 4 seconds. So what was the change in displacement here? Well, where did we start from in part 3? We were at 8 meters, right? 8. And we ended at 4. And remember, anytime you take the change in something, it's final minus initial. In this case, 4 meters was our final position and 8 was our initial. So it's 4 minus 8. And how long did it take to do that? 4 seconds. So the time elapsed was 4 seconds. So we have minus 4 meters in 4 seconds. So the average velocity in part 3 was negative 1 meters per second. The negative represents the student moving back toward the starting point. So in leg number 1, they were moving away, so they had a positive velocity. In part number 3, they were moving back, so they had a negative. And you can see that by the slope of these lines. This slope is positive. It's moving up and away. However, this slope for part number 3 is negative. It's moving down. So that tells us, just by looking at these, part 1 has a positive slope and part 3 has a negative slope. If there is no slope at all, part 2 and part 4, velocity is 0. If it's flat, velocity is automatically 0. Go ahead and take a guess as to part 5. Is this going to be a positive velocity or negative velocity? It's going to be positive. The slope is going up and away. This is going to be a positive velocity. And let's calculate it. So, the ending displacement for part 5 is 14 meters. And the starting displacement was 4. Remember, we moved down to 4 meters in part 3. And the time it takes to go from 4 meters to 14 meters is 5 seconds. So, our change in position is going to be 10 meters, and it takes 5 seconds to get there, so the total velocity is 2 seconds. And it's positive, just like we predicted. So let's double check our numbers here. For part 1, 0.8 meters, part 2, 0, part 3, -1, and the negative is really important. Part 4, 0, and part 5, 10. Ta-da! So now that we have all of this information for velocity, what do we do with it to make a velocity versus time graph? Well, what you need to do is, first of all, draw your axes. In a velocity versus time graph, it's similar to displacement versus time. Time is on the bottom, measured in seconds, but instead of displacement on the y, we have velocity measured in meters per second. All right, so let's try our hand at this. Interval number 1. What was the velocity during interval number 1? It was 8 meters per second, or 0.8. So that's about right here. And how long was he moving at 0.8 meters per second? Well, for 10 seconds. So let's count these as 2s. 2, 4, 6, 8, 10. 10 seconds. So what does that mean? Did he angle up at all? Did he go down? It turns out for velocity, it's going to be a flat line. And this means he stayed moving at 0.8 meters per second for those entire 10 seconds. If we were to make a line that sloped up like this, that would mean he was speeding up. And he wasn't speeding up or slowing down, he was moving at a constant velocity. So that is what the first leg looks like. All right, part number 2. How fast was he moving in number 2? What was his velocity? It was 0. Okay, so where is 0 on our graph? Well, 0 is right here, at 0. Velocity is 0, right here. And how long was he there for? 10 seconds, again. So 2, 4, 6, 8, 10. This was the second leg of the journey, on the axis for 10 seconds. Part number 3. His velocity for leg number 3 was -1 meters per second. So where's -1? Well, we need to extend our axis here to make this work, right? Negative numbers are below the 0 line. So for this third part, he was at -1. And how long was he here for? 4 seconds. So he was here for 2, 4, right here. So he starts right at this time, and he moves at -1 meters per second for 4 seconds. Let's make this longer. The next leg, how fast was he going? 0. So again, we're at 0, right here. And he was there for 6 seconds. So 2, 4, 6. So So you may have noticed for velocity graphs, unlike displacement graphs, you do not connect the lines from where they end to where they begin. So this line is from leg 1 to leg 2 is not going to look like this. It's not going to be slanted. You move the entire line over to the velocity and you draw a flat line at that point during the time interval they were traveling at that velocity. Okay, so the last one, leg 5, is he was going 2 meters per second, so that's right here, and he was going for 5 seconds, so 2, 4, 5. So right here, 2 meters per second for 5 seconds from where he ended when he was not traveling and standing still, and that's the last leg of the journey. So this is what the velocity versus time graph looks like for that same displacement versus time graph. All right, let's see if I can superimpose. So I'm going to try and bring this displacement graph over to the same page as the velocity graph so we can compare them. All right, so on the bottom is our displacement versus time graph, and on the top is velocity versus time. And you can see some similarities here. It's all about the slope. So when you're going from displacement to velocity, look at the slope of your lines. Here, the slope of this line is positive, so the velocity is going to be positive. At parts 2 and 4, the velocity is, or the slope of this line is 0. Therefore, the velocity is also going to be 0. At point 3, your slope is negative, so your velocity is negative. And at point 5, your velocity, or your slope is positive, so your velocity is positive. It turns out, if you were to calculate the slope of these lines, say calculate the slope of line number 1, you will get velocity. So if you were to mathematically find the slope of part number 1, you would get 0.8, positive 0.8, which was your velocity for the first leg. You can calculate it either way. You can use your displacement equation for the displacement moved and the time elapsed, or you can do a mathematical slope. It turns out they're pretty much the same thing, because once you put units in for your y and your x, you're doing the same thing. You're calculating the rise over the run, or change in displacement over change in time. It's the same thing. So some questions to discuss. Well, what does it mean to have a negative velocity? Does it mean you are moving back toward the origin? Well, let's see. Negative velocity here was in leg number 3. And what kind of movement was that? It was back toward the origin. So a negative velocity means you're moving back toward where you came from. Can displacement be positive and velocity be negative? Well, let's see. Where was our velocity negative? At point 3. If we look at point 3 right here, is our displacement negative? Our change here is, but overall it's positive. So yes. So when might you have a negative displacement and a positive velocity? Well, if you're moving forward faster than you move back, even though you end behind your starting point, you will have a positive average velocity and a negative displacement. So say you're moving forward 5 meters at 10 meters per second. Both of those are positive. But then if you turn around and head backwards for 10 meters at 1 meter per second, you will have ended up behind your starting point, so you have a negative displacement. However, you moved forward a lot faster than you moved back, so your average velocity is going to be positive. And finally, can distance or speed ever be negative? This should be B. Well, distance and speed are scalars, remember? And scalars do not have direction, only magnitude. So distance and speed will never be negative. They are always positive numbers because it doesn't matter what direction you're going in. So your homework for tonight is to read the speed and velocity page and answer this question. Make a velocity versus time graph that corresponds to the following displacement versus time graph. So here we have displacement versus time, and you need to calculate the velocity for each leg of the journey and then make a velocity versus time graph that matches this.